This is calculus, the second part of lesson 3, which is on integration of inverse trig functions. So we remember, for example, if you differentiate the arcsine of x, the inverse sine of x, that's 1 over the square root of 1 minus x squared. And if you differentiate the arc cosine, it's minus 1 over the square root of 1 minus x squared. So really what that means, if you had to integrate 1 over the square root of 1 minus x squared, the antiderivative would be arcsine x, or equally minus 1 over the square root of, minus the arc cosine of x, plus a constant. And usually to make things simple, we pick one or the other of each pair. So in general, if you have the integral of 1 over the square root of a squared minus u squared, if you factor out the a and make a substitution, you get this as arcsine of u over a. So this is the 3 integration formulas that lead to inverse trig functions. So this is what leads to the arcsine. And here's an example. If you take the integral of 1 over the square root of 4 minus x squared, 4, a squared is 4a is 2. So this is just arcsine of x over 2 plus c. That's pretty easy. The arctangent, the derivative of the arctangent of x is 1 over 1 plus x squared. So the integral of 1 over 1 plus x squared is the arctangent, or more generally, the integral of 1 over a squared plus u squared is 1 over a, arctangent of u over a. So here's an example of an integration of this form. A little more complicated because it's a little more interesting. 1 over 2 plus 9x squared. So first of all, I want it to look like a squared plus u squared. So 2 is the square root of 2 squared. And 9x squared is 3x squared. And if I were going to make a substitution, u equal 3x, I would need a 3 in the numerator. So I can put a 3 in the numerator if I put a 3 in the denominator. So you can check these two things are perfectly equal. And if I substitute u equals 3x, so du is 3 dx, this becomes 1/3 du over root 2 squared plus u squared. So by this formula, a formula for that gives an integral equal to an arctangent. This is a third, that doesn't change. A is root 2, so 1 over root 2, arctangent of 3x over root 2. The third inverse trig function is the arcsine, and the derivative of the arcsine is 1 over the square root of x squared minus 1 times x. The corresponding integration formula is the integral of 1 over u times the square root of u squared minus a squared is 1 over a, arcsine absolute value of u over a. Again, as always, plus a constant. So here is something that is of this form, dx over x times the square root of 4x squared minus 9. I can write 4x as the quantity 2x squared, and 9 is 3 squared. So this looks like u squared minus a squared, where u is equal to 2x. I'd like to have a 2x here. I can put a 2x. If I put a 2 here, I have to put a 2 there. Okay, that's fair enough. And now if I make the substitution, if u is 2x, du is 2 dx. So this is equal to the integral of du over u square root of u squared minus 3 squared. That's exactly this formula, with a equal to 3. So you get a third, the arcsecant of u over 3. U is 2x. That's what we get. So these are integrals which lead to inverse trig functions. Now, they're not always, this may not be easy, but they're not always, they're usually harder. Or you have an interesting integral and you have to be a little bit more clever about putting into the form of something that you know how to integrate. So here's an example which doesn't look like an inverse trig function at all in the beginning. The integral of 1 over the square root of e to the 2x minus 1. Now, if we make the substitution u equal x, then e to the 2x is u squared. That's what we have here. So this is like the square root of u squared minus 1. If u is e to the x, du is e to the x dx. So, but I don't have an e to the x dx, I just have e to the x. But if I multiply and divide by e to the x, I haven't changed anything. Now when I substitute u equal e to the x, this is du over u times the square root of u squared minus 1. That's exactly my arcsecant formula. You get arcsecant of e to the x. You don't need the absolute value sign because e to the x is always positive, plus c. So this is example 2 in this section of the text. And you have to be a little bit clever and lucky and work to figure it out. Sometimes, well, there's just a range of techniques that people have developed over the centuries to do integrals. Sometimes you have to split one integral into 2. So suppose I have the integral of x plus 2 over the square root of 4 minus x squared. You can try to do it directly. If you succeed, great. If not, you could split it up as 2 integrals. The integral of x over the square root plus the integral of 2 over the square root. And then we do those 2 integrals separately. If you look at this, it should be clear that a substitution u equal 4 minus x squared will solve the problem for you. So for this first integral, I'll call this 1, and this is 1. I'm going to let u equal 4 minus x squared. So then du is minus 2x dx. So if I multiply top and bottom by minus 2, I get minus 1/2 du over the square root of u. But that's the 1/2. U to the minus 1/2, the integral of that is 2 root u. So this is just minus root u, or minus square root of 4 minus x squared. That's what that becomes. And what about the second integral? Well, this is exactly of the form of the arc sine. I have 2, I can take the 2 outside. This is just the integral of arc sine of x over 2. So I know what this is, I know what this is, namely this and this. I add, and that's the answer. There's one more technique which is useful, which involves what is called completing the square. So completing the square means if you have x squared plus bx plus c, I want to make that a perfect square plus a constant. And I can make this a perfect square by adding and subtracting b squared over 4. So I plug in a plus b squared over 4 and a minus b squared over 4. So this really is an equation. And this is a perfect square. It's x plus b over 2 squared minus this. So here's an example. I have the integral of 1 over x squared minus 4x plus 7. I complete the square. X squared minus 4x plus 7, that's x squared minus 4x plus 4 plus 3. Why 4 plus 3? Well, 4 plus 3 is 7, and x squared minus 4x plus 4 is x minus 2 squared. So this is equal to the integral of 1 over x minus 2 squared plus 3. That's exactly the arctangent, well, 1 over root 3. 3 is root 3 squared. Arctangent x minus 2 over root 3. So that's a nice example of completing the square. And there are a few homework problems that will require that. Okay. So that's as much as we do in chapter 5. We skip chapter 6 for the moment. We'll come back to that in about a week and a half. And we jump to chapter 7, which is on applications of integration. And the first application is calculating the area between two curves. So let's say we have a function y equals f of x, and another function y equals g of x, and there's this region between them. And we want to calculate the area. So in the simple case that I've drawn here, where both functions are non-negative, the integral from a to b of f of x is the area of this whole region. And the integral of g of x is the area of this region under the curve g of x. So if I take this area and subtract this area, I get what I want. So the integral that expresses the area between these two curves is the integral from a to b of f of x minus g of x dx. So here's an example. Find the region bounded by the following curves. Y equal x squared plus 2, that's a parabola. Y equal minus x, that's a straight line. X equals 0 and x equal 1, those are two vertical lines. So if we draw that region, I haven't drawn it, well, not drawn to scale, but from 0 to 1, this is the line y equals minus x. This is from the parabola y equals x squared minus 2. I mean, the parabola would really look like this, and this line would continue. But the region between these curves that we're interested in, it's that region. And so the area is the integral from 0 to 1 of the curve on top, x squared plus 2, minus the curve on the bottom, which is minus x. So this is the integral from 0 to 1 of x squared plus x plus 2. We integrate that, that's 1/3 x cubed plus 1/2 x squared plus 2x, evaluated from 0 to 1, which is 1/3 plus 1/2 plus 2 minus 0, which is 2 5/6, or 17 over 6. Okay. We'll do a few more of these. Let's look at the region bounded by the curves 2 minus x squared and x. This is a parabola that's opening down, and this is just the line y equals x. The straight line y equals x, this is minus 2, 0, 2, minus 2, plus 2. That line. 2 minus x squared, what does that look like? Well, at 0, it's equal to 2. At 1 and minus 1, it's equal to 1. At plus and minus 2, it's equal to negative 2. So the graph looks like that. So this is the graph of the parabola. This is the graph of the line. And this is the region in between them. So the area is equal to the integral. See, these lines intersect where? Here is the point minus 2, 2, minus 2, minus 2. It's the point 1, 1. So it's the integral from negative 2 to plus 1 of the curve on top minus the curve on the bottom. That's the integral. Well, I can just write it down. That's 2x minus the third x cubed minus a half x squared, evaluated from minus 2 to 1. What is that equal to? When x is equal to 1, that's 1 minus a third minus a half. And when x is equal to negative 2, I get 2 times negative 2 is minus 4, minus a third times negative 2 cubed, which is minus 8, minus a half times negative 2 squared, which is 4. So this is 1 minus 5/6, that's 1/6, minus 4 plus 8/3 minus 2. That's 8/3 minus 6. 6 is 18/3. So it's minus 18/3 plus 8/3. That's minus 10/3. So this is minus 1. This is 1/6 plus 10/3. 10 is 20 over 6 minus 1 is, let me just double check the arithmetic. So I'm integrating 2 minus x squared minus x from minus 2 to 1. The integral is 2x minus a third x cubed minus a half x squared from minus 2 to 1. So when x is equal to 1, I should do the arithmetic correctly. 2 times 1 is 2, minus a third minus a half. So this is 2 minus 5/6, which is 7/6. So this is 7/6 plus 10/3. That's 7/6 plus 20 over 6, that's 27 over 6, which is 9 over 2. So the area between these curves is 9/2. Here's an interesting question. Look at the sine x and the cosine x. These are oscillatory functions. And let's just take a look at what the graph looks like. So let's say this is minus pi, 0, pi, 2 pi. The sine, and they both go from minus 1 to 1. So the sine looks like that. Y equals the sine of x. And the cosine, let me draw that in red to make it a little bit clearer. Cosine looks like that. And they cut out various regions. I mean, infinitely many regions, they repeat. But let's just try to find the area of this region. Just one of these places, one of these pieces, regions in the plane, cut out by the sine and the cosine. So to do that, we have to know where do the sine and the cosine intersect. So when does sine of x equal cosine x? And this is exactly at pi over 4. So the sine of pi over 4 is 1 over root 2, which is the same as the cosine pi over 4. And this point where the sine and the cosine intersect is 5 pi over 4. The sine of 5 pi over 4 is minus 1 over root 2. And that's also the cosine of 5 pi over 2. So this point is 5 pi over 2. And the area we want to find then, from pi over 4 to 5 pi over 4, the sine is bigger than the cosine. So the curve on top is sine x, the curve on bottom is cosine x, and we're doing that integral from pi over 4 to 5 pi over 4. We know the integral of the sine and the cosine. The integral of the sine is minus the cosine, and the integral of the cosine is plus the sine. So we're integrating minus cosine x minus sine x from pi over 4 to 5 pi over 4. Or I can take out the minus sign, that's minus cosine x plus sine x from pi over 4 to 5 pi over 4. That's equal to what? Minus, at 5 pi over 4, the cosine and the sine are both equal to minus 1 over root 2. So this is minus 2 over root 2. And I subtract from that the value of cosine plus sine at pi over 4. At pi over 4, they're both equal to 1 over root 2. So this is minus 2 over root 2. So the minuses cancel. We get 4 over the square root of 2, which is 2 times the square root of 2. So this area between the sine and the cosine is equal to 2 over root 2. Okay. We'll do one more problem. The region between this cubic curve, this is 3x cubed minus x squared minus 10x, and the parabola minus x squared plus 2x. Now, if we could use Maple, it'd be easy to graph this function. But if we want to try and figure out how to solve this by hand, let's see. F of x is 3x cubed minus x squared minus 10x. I can factor out an x. I get 3x squared minus x minus 10. And can I factor this? Well, if x equals 2, I get a root. So this is x times x minus 2. And if I divide x minus 2 into that, what do I get? I should probably get 3x plus 5. Let's just check. If I multiply these two, I get 3x squared minus 6x plus 5x is minus x minus 10. So this is x times x minus 2. Let me factor out a 3, x plus 5/3. So that says if I graph the cubic, it's equal to 0 at 0, at 2, and at negative 5/3. So this cubic goes up, comes down, goes up again. How do I know that? Because a cubic always has that same up, down, up behavior. So that's the curve y equals f of x. What about g of x? Well, g of x is minus x squared plus 2x. So that's a parabola that opens down. If I put in minus 1 plus 1, so then this is minus x squared minus 2x plus 1 plus 1. Or I'll write this as minus x minus 1 squared plus 1. 1 minus x minus 1 squared. That's a parabola that's opening down, and it has this vertex at x equal 1. And when x is equal to 1, it has the value 1. When x is equal to 2, it has the value 0. When x equals 0, it has the value 0. So this parabola looks like that. So this is the graph of y equals g of x. And we'll see that if we want the area between these two curves, there's two parts to it. There's this part where g of x is bigger. G of x is on top, f of x is on the bottom. And there's the second part where f of x is on top and g of x is on the bottom. And of course, we have to know, where do these two curves intersect? They intersected 1 at 0, and what about over here? Well, to do that, we have to solve the equation. When does f of x equal g of x? That is, when does 3x cubed minus x squared minus 10x equal minus x squared plus 2x? So that's the same as 3x cubed minus 12x equals 0. Or divide by 3, x cubed minus 4x equals 0. Or x times x squared minus 4, which is x minus 2, x plus 2 equals 0. The roots are at 0 and plus or minus 2. So here the y coordinate is minus 2. And when x is negative 2, this is negative 8. So what is the area of the region we want? Well, there are two parts to it. The green region, that's the integral from minus 2 to 0 of f of x minus g of x dx, plus the red region, that's the integral from 0 to 2 of g of x minus f of x dx. But these are just polynomials. It's easy to do those integrals, and it's also done in the text, so I don't need to do it here. So, good. So this is the first application in chapter 7 of integration, to use integration to find the area between two curves. And we get very, very pretty pictures and very nice geometrical results. And that's it.